Today we're going to review Unit 4, which was transformations and rigid motions. We're also going to review things like dilations and equations of lines in this day as well. So first of all, two figures are considered congruent if there exists a series of rigid motions which map one to the other. It's important to know that rigid motions preserve distance of segments and angle measure. Okay, three rigid motions, if you think about it, are reflections, rotations, and the one that you're seeing over here on the right is a translation, where it's just sliding it really across the grid. Okay, the original figure is called our pre-image. Pre meaning before, so this is your before image, and then your image is your after. Okay, so when I ask for the image of something, I want the after the transformation. Starting with rotations, first of all, know that rotating 90 degrees means you are rotating counterclockwise 90 degrees. Negative 270 would be in the other direction. Negative is a clockwise rotation. So actually, let me zoom in here for a second. So if I had like a little axis in here, okay, this would be a positive 90 rotation. In the other direction would be a negative 270 rotation. But you'll see that you end up in the same spot. So with that being said, the rules are actually the same. Okay, the way I remember the rule here is I switch the order, and whoever goes into the first slot becomes negative. So notice how X and Y switch locations. Since Y moves to the first slot, he becomes negative. So for example, with the point 2, negative 5, I switch it, and then I negate whoever goes into the first slot. So negative 5 is now positive 5, and then the 2 remains the same. Okay, 180 and negative 180 is the same rotation, and this is about the origin again, just to re-emphasize that. If I rotate another 90, which would total 180, you're seeing these coordinates now flip, and the x becomes negative. So 2, negative 5 is now negative 2, positive 5. So again, they're switching. Whoever goes into the first slot is negative. Lastly, 270, which is the same as negative 90, is where they switch again, one last time, and then the y becomes positive. So it's going to be, or I should say the y doesn't change. It becomes negative 5. Whoopsies, I wrote this wrong. So essentially it's like this. Oh no, I wrote it right. Essentially it's like this. If I took this image before and I switch x and y, this moves into the first slot, so it's now negative. And then the negative 2 would just change here, which is what you're seeing as well with this rule. The y remained the same as it was. The x became the opposite sign. Okay, you don't really need to memorize these. If you know this one, the first one, you can always derive the next two by just keep doing the rotating of 90 rule. If we rotate a point not about the origin, we have to use negative reciprocal slopes to help us. So for example, zoom in here, if I'm going to rotate A 90 degrees about point B, keep in mind 90 degrees would be moving that way, counterclockwise. So if I look at the slope from A to B, it looks like it's a slope of positive 2, because I go up 1 over, up 2 over 1. Okay? In order for it to be rotated 90 degrees, this must be 90 degrees. Okay? In order to create a 90-degree angle, you must have negative reciprocal slopes. So the new line I'm going to create has a slope of negative 1/2, and in the same distance. So I'm going to go back to up 1, and you can see how this slope would be negative 1/2, therefore that's 90 degrees. And this distance is the same distance here, so that's your A prime. So A prime is 0, 2. There's no rule for that. It's really just knowing your negative reciprocal slopes. All right, one other thing about rotational symmetry, a couple things to know are order and magnitude. The order is the number of times a figure maps onto itself in 360 degrees. Magnitude is the smallest angle it takes to map that first time. So in order to do this, I have a little video, so 1 second. Okay? 1, 2, 3 is the number of times this figure, which is in your notes, mapped onto itself when the figure was rotated 360 degrees. So that means the order of it is 3. Magnitude is the number of degrees it takes for it to map onto it the first time. So if it mapped onto itself 3 times and there's 360 degrees on one rotation, it takes 120 degrees, there you go, that's 120 degrees, in order to map onto itself the first time. So that's the magnitude. Okay, so again, order is 3 here. Magnitude can be calculated by 360 divided by the order, which 360 divided by 3 is 120 degrees. Okay, a few more rules here. If you're reflecting in the y-axis, you negate x. So this point here, 2, -5, becomes -2, -5. If you reflect in x, that means you negate y. So this point would become 2, 5. Y equals -x just switches them. So this is -5, 2. And just so you guys are clear, I'm doing this point every time. And y equals -x switches and negates them. So this becomes 5, -2. Reflecting in the origin is the same as rotating 180 degrees. You'll see that's the same rule. So they just become negative, or the opposite, I should say. They're just negated by -1. And lastly, with a translation, you just take whatever this vector is, add the a to the x value, add the b to the y value. So let's say I took the point 2, -5, and I translated -310. I would do 2 plus a -3, -5 plus 10. Okay, and that's -1, 5, and that would be your image. Now, a transformation that is not a rigid motion is a dilation, and that's because distance is not always preserved. Okay, angle measure is though, so therefore figures that have been dilated are always similar to their original figure. So we make sure you know when you're dilating about the origin, and a scale factor can always be figured out, that's an R value, by doing image over pre-image. If you're dilating by a scale factor of R, you're just multiplying the coordinates by that scale factor. And again, this is strictly when it's about the origin. So for example, let's say I took this point and I dilated it about the origin with a scale factor of 2, its image would be 4, -10. So all I did was multiply the x and y by 2. Dilations not at the origin take a little bit more work. If it's not at the origin, you have to measure the distances to determine the scale factor. A dilation must be described with a scale factor and a center, so if you're asked to describe something, it is important that you state its center of dilation. And the center of dilation, then, just remember, is that fixed point for which the points are all expanded or contracted. So let's say I take this triangle and I dilate it about the point -5, 5 with a scale factor of 3. So I'm going to zoom in here. So -5, 5, 1, 2, 3. Okay, here, 1, 2, 3, 4, 5. Okay, so this is my center of dilation, and I'm going to dilate everything with a scale factor of 3. So what that means is F's distance to the center of dilation is now going to triple. So if the distance to the center of dilation is 1 currently, 1 times 3 is a distance of 3. So that means F is now going to be 1, 2, 3 units away. So that's now your F prime. Okay. Going this way, G looks like it's 1, 2, 3, 4 units away. So now 4 times 3 is 12, so I should now be 12 units away. So 4, 5, 6, 7, 8, 9, 10, 11, 12. So that means here's your new G prime. Okay, and right now, if I draw a line in here, that's your one side so far of your triangle. Okay, as far as H goes, I just have to count my slopes. It looks like I'll go up 1, 2, 3 over 1, 2, 3. So I'm just going to have to copy that pattern 2 more times. 1, 2, 3, 1, 2, 3. Hopefully I counted that right. And then 1, 2, 3, 1, 2, 3. Okay, so now this is going to be your new H prime. I can go in and put the rest of my lines in there. Okay, and there you have it. So the resulting figure is going to be similar to the original figure. So the image is similar to the pre-image because angle measure has been preserved. They are not congruent though because distance has not been preserved. Each of these distances are now 3 times the length of the original pre-image. Okay, last thing to remind you guys of, because you definitely will see a question like this somewhere on your test in June, the pre-image of a line is negative x plus 3, and we want to determine each transformation after certain dilation. So if I want to determine the equation of the image after a dilation about the origin with a scale factor of 2, what you need to remember is that slope is always going to remain the same, but your y-intercept is going to change in this case. So for example, your line is going to have a y-intercept of 3, slope of negative 1. So this is just a rough, so I'm going to zoom in here. So y-intercept of 3, slope of negative 1. Okay, so it roughly looks like this. Okay, we're going to take this y-intercept, which is here at 0, 3, and dilate that by 2. So 0, 3 now becomes 0, 6. Because I dilated about the origin. I've doubled the distance from the origin. Slope will still remain the same. Okay, so it's a resulting parallel line. So coming back over here, my resulting equation is y equals negative x, but now it's plus 6. And again, that's because I dilated about the origin. What about if I dilate about the point 0, 3? Okay, well the point 0, 3 is actually on the line. So if the point is on the line, every location of that point is just going to end up, every pre-image point on this line is just going to end up on a new location on the same line. So if the center of dilation is on the line actually remains the same. So we're still going to have y equals negative x plus 3. So again, think about that. If you were to take this point and dilate it about itself, it's not going to move. And this point would move, but it would just move to a new location, but still on that same path. So the line does not change. Lastly, determine the equation of the image about the point 1, 1 after a scale factor of 3. Now it's very similar to what we did in the previous problem where we have to count our distances. 1, 1, let me zoom in here, is right there. So what I do is pick a point here and realize, all right, well, this is a distance of 1, but now it's going to be triple the distance. So here's a new location. Okay, this way I have a distance of 1, I'll triple it. Slope will still remain the same. Okay, and then by getting those 2 points, I can work backwards to figure out the y-intercept, which appears to be 5. Okay, because I knew the slope had to remain the same because angle measure is always preserved in a dilation. So, slope is still the same. Y-intercept is now 5. So therefore, the equation of my line is y equals negative x plus 5.